Let us start. So we were discussing about the sources and sinks, and then there is one more concept called doublet. So this doublet actually, so if you know the electric fields, right? So there is something called dipole. So wherein the positive charge and negative charge comes together but separated by almost very minor distance. So exactly the same concept. Whatever we discuss in case of electric fields, same thing as it is you are going to get it in fluid dynamics. So there is no difference at all. Fluid dynamics analysis and electric field analysis, because both are dealt with the fields and both are dealt with the dipoles and both are dealt with the point charges. So point charge is nothing but a source, and then negative charge is nothing but a sink, and coming together is nothing but a dipole in electric fields. The same thing we call here it as doublet. Got it? So here doublet we mean, suppose this is x-axis and this is y-axis, and then there is a source of strength. So a source of strength m here and a a sink of strength minus m here. So these two are separated by a distance of ds, where ds is almost 0. And this system of arrangement, so a doublet is nothing but the system of arrangement of a source of strength m and a sink of strength minus m, which are separated by an infinitely small distance. By an infinitely small distance, and satisfying the condition of the product of m into ds getting a definite value, getting a finite value. Is called a doublet. So here ds is almost tending to 0, but m is tending to infinite. But the product m into ds is a finite value. A finite value. So this mu is called as the strength of the doublet. Got it? That is the strength of the doublet. So this is the concept of doublet. This is exactly 100% same as the dipole. So no difference. A source and a sink, both are separated by an infinitely small distance, and to have a finite value for this doublet magnitude, so this m should be so high and this ds should be so low. The product should be a finite. Got it? That is the condition. Note down this. Now, what is the complex potential of this doublet? So exactly we follow in the similar lines, the way we have derived, right? The same thing we'll be reusing it here. So here let us consider a random point here. So this is at a distance of r from the origin, and this is at a distance of r plus delta r. Now here, so the projection, okay, so ds is, so this is ds and this is r plus delta r, and then the complex potential W at this point, because of this source, this sink of strength minus m, will be m log z. So this is the point z where we wanted to identify the complex potential. And then same thing, because of this source, here the complex potential will be minus m log z plus delta z. Z plus delta z. So if you separate these two together, what we can do is separately we will calculate the the scalar potential at point P So the scalar potential at point P due to the sink of strength minus m located at origin will be, so this we have already calculated, phi is nothing but m log r, right? Is this the one? Can you cross check it? Yesterday I derived it. Yeah, this is correct one, m log r. And then the same thing, so this is because of the sink. And then phi due to source, this will be minus m log r plus delta r. So this is due to the other part. So that is because of the source at this location, the complex, so the scalar potential will be this one. So minus m log r plus delta r, where this is complex potential can be expressed as phi plus I psi. Now in this actually phi we are calculating separately, and then based on that we are going to calculate the psi value. Now here the total potential, total scalar potential at P, so this will be the sum of both, that is m log r minus m log r plus delta r, and then this is minus m, if you take it out, log r plus delta r minus log r. Then this is minus m log r plus 1 plus delta r by r. Now if you expand with the help of log 1 plus expansion, 1 plus x expansion, this will be minus m log of, so this can be x is the first term. So x is nothing but delta r by r. So approximated to first term. Of log 1 plus x expansion. So here minus m log delta r by, minus m into delta r by r. This delta r by r actually we have got from the expansion of log 1 plus x expansion. So wherein log 1 plus x is equal to x minus x square by 2, like that you are going to get it. But the higher order terms actually we have neglected it, and we took only the first component. So without losing any accuracy, because delta r is so small that it is very, very minor to notice, because both are separated by a very minor distance, almost ds tending to 0. Got it? Then, so ds, so if this angle is theta, then ds cos theta is nothing but dr. So dr ds cos theta. So if you replace this value here in this equation, that is the total potential is equal to minus m into, so ds cos theta divided by r. And then the product of these two, we have given a separate name, mu is equal to, which is nothing but the strength of this doublet, delta S into m. So this is what we treated as mu, which is nothing but the strength. So if you replace this, then this is minus mu cos theta by r. Got it? This is the scalar potential at the point P because of the doublet, which is located at the origin and whose axis is along x-axis. So axis of doublet. X-axis. Got it? So the axis of doublet we mean on which line it is there. So this is what we call as the axis of the doublet. So here, see this, I hope you understood till this point. So this is further simplified, minus m log r plus delta r, and then this log r. So log a minus b will be log a by b. So we have got r plus delta r divided by r, and r by r is 1, and delta r by r I kept it as it is. And then this is as if like log 1 plus x expansion. Now the log 1 plus x expansion with the help of Maclaurin series will be, so this is x minus I think plus x square by, what is log 1 plus x expansion? Yeah, so x minus x square by 2. X minus x square by 2 plus x cube by 3. Like that, actually the expansion will continue. In that, we have neglected the higher order terms because dr, so this dr is almost 0. So this 0, if you square it, it will be far, far lesser than 0. That's why, without losing any accuracy, we can neglect this higher order parts and we can treat only the first part x. So in place of x, here it is delta r by r. So that's why minus m into log 1 plus delta r by r can be treated as delta r by r simply. Understood this one, Anjali? So once you understand this, then this is dr, actually I expressed in terms of ds, right? So dr is nothing but the difference between these two. That means, so if you draw a perpendicular from this, so this part from here to here is nothing but delta r. So this can be expressed as ds cos theta. So dr is equal to ds cos theta, I kept it. Got it? So if you draw a perpendicular, then this is a right angle triangle. So on this right angle triangle, this is ds length and this is dr length. And then ds cos theta will be the dr equivalent. Understood? Any questions on this? I hope everybody understood. Now then, so m into ds you can treat as mu, because this is nothing but what we have defined for the doublet to be the strength of the doublet will be m into ds. So this is the strength of doublet which we will represent with the help of mu. So this is a mu letter. So then mu cos theta by r. Got it? Noted down till this point? Okay. And then phi value we got it, the magnitude of phi. mu cos theta by r. Then, so for constant potential lines, for equipotential lines, phi you can treat as constant. So that's where we treat all the potential magnitudes will be constant, where the curve phi is equal to constant. Now this, if you equate to the constant, then the equipotential line will be mu cos theta by r is equal to constant. And this constant, so if I multiply on either sides with r, so this is r cos theta, so mu into r cos theta is equal to c into r square. Now this can be mu x is equal to c into x square plus y square. So this is nothing but the equation of the circle. So this is an equation of the circle. So this can be treated as x square plus y square minus mu by c into ex is equal to 0. I hope you are aware of this is the equation of the circle. And what kind of equation of the circle it is? What is the shape of the circle? So this is as if like, so on y, so this is 0, and then x is shifted to mu by c, right, or mu by 2c. So that is somewhere here actually you will find the center, and then this circle will be like this. Got it? So this is the shape of the circle, right? So this kind of circles, these are not ovals, so these are circles here. So these are the kind of circles where it touches the y-axis and center is located on the x-axis. So it will be keep on increasing like this. Got it? So for different values of c, you are going to get different kinds of circle. And then correspondingly, so these are actually equipotential lines. Equipotential lines that are generated because of the doublet of strength, minus m here and plus m here. Got it? So this is ds. So because of this doublet, the equipotential lines that are generated are this one. Obviously, perpendicular to this actually you are going to get the streamlines. So the streamlines equation we can derive it from this. So we know the Cauchy-Riemann equations. Dou phi by dou r is equal to 1 by r into dou psi by dou theta. So phi value actually we got to know that mu cos theta by r, and then dou phi by dou r you can calculate it and then equate to dou psi by dou theta into 1 by r. So from there we can integrate it and we can get the value of psi. So note down this, we are going to do that. This is minus. So even if it is minus, then mu constant can incorporate that negative sign. Then okay. So from the CR equations, this is CR equations. So 1 by r into dou psi by dou theta dou by dou r of, and this is minus mu into cos theta into, so dou by dou r is minus 1 by r square, and then this is 1 by r you can cancel it out. Dou psi by dou theta is equal to mu cos theta by r. And then dou psi is equal to mu cos theta by r into dou theta. So integrate on either sides. Psi you are going to get it as mu by r into derivative of, so integral cos theta, that is sin theta, right? So this is the psi magnitude. Yeah. So this is phi and this is psi. So the complex potential W will be phi plus I psi. This is the complex potential. So this is phi and this is psi. Got it? If you want to write it together, then this will be phi plus I psi. Phi is minus mu cos theta by r plus I times of mu by r sin theta. So this is, so if you take minus mu by r, then this will be cos theta plus I minus I sin theta. And this is minus mu by r into cos theta minus I sin theta will be e power I theta as per Euler's theory. So a power minus I theta. So this is minus mu by r into e power I theta. So this is minus mu by z. So this is nothing but the complex potential. Okay, so the sign change is coming just because actually he treated different value of theta. Let me explain that. This is sink of strength minus m. This is source of strength m. So this is the doublet. Now if you consider this point, then earlier actually we treated this as theta, but in the textbook what he treated this as theta. So if this is theta, then this will be phi minus theta. And then from this, if you want to find out this magnitude perpendicular, so this you can even treat as this one. So this length dr, delta r is coming as cos of phi minus theta. This is equivalent. Got it? So this angle is phi minus theta, but so cos of phi minus theta will be r plus delta r. So that's the reason. So this is minus cos theta. So hence actually he treated this as plus, and then this is also plus, and this will be plus, and this will be minus. Plus, yeah, this is minus only, this is plus, yeah. So this is also plus, and this is also plus, and this is also plus. Mu by z is the strength of the doublet. Got it? No? See this, just the sign change. So this angle is theta, and obviously this angle will be d theta. And then this is r, this entire length is r, and this length is r plus delta r, right? So r plus delta r, this delta r, so in this particular case, where we have treated r plus delta r is the lesser value and r is the more value in this case, correct or not? So here delta r you are going to get it if you subtract from this value this length, right? So this is the delta r value. So which you can get it if you draw a perpendicular from this. So this entire length is delta r, this entire length is r, and this length is r plus delta r. That means if you, from r if you subtract this length, you are going to get the this r plus delta r value. Got it or not? So if you want to get this value, so this value, so this is as if like if this angle is theta, then this angle will come as pi minus theta. Now cos of pi minus theta is nothing but the projection. So suppose this is ds length, and you project this onto the cos of pi minus theta on this value. This magnitude, whatever you are going to get it is equivalent to dr. Got it or not? So this is simple triangle. You can analyze it. You are going to get it. Got it? So that is only the convention, where in the previous derivation we have treated this as theta, And here actually in the textbook what he has treated is this as theta. That's the only difference, nothing more than that. Got it? So this is about the doublet. So here the essential thing what we need to remember is only the strength of the doublet is nothing but mu by z, where mu is so mu is strength of doublet and mu by z is nothing but the complex potential of the doublet. W is equal to mu by z. So this is one of the important relations. So for a source, it is W is equal to minus m log z. For a sink, it is W is equal to plus m log z. So this is the complex potential of a source, and this is the complex potential of a sink, and this is the complex potential of the doublet. So this is the doublet. So these are the important things actually that you have to remember. Clear? Any questions on this? Note down one problem. Or actually I will explain the method of images also, then we can go to the problems. Method of images. So this method of images, suppose let us say this is the wall of a dam. Now on this, so here let us say there is a source of strength plus m here. So because of this source, right, so the fluid is continuously produced there, and then this is continually distributed this way in all the directions radially. Right? So this is how the fluid is trying to distribute in this format. But here there is a hurdle here. So this is nothing but the wall of the dam. Now here, if you wanted to analyze the complex potential or the field lines or the stream function at any point, right? So how you are going to deal with? Suppose if there is a water on the right side also, and then so here if you wanted to analyze here it is a dam. Now ideally, if you try to find out the complex potential here, it is of no meaning because there is a hurdle here. Got it or not? Understood? So the complex potential because of this source, so is at any instant, even if you find out any locations on this entire plane, right? So you are going to get appropriate value because that's what we have derived. But that is before this wall. After this wall, if you say that the complex potential of the fluid that is getting produced at this location is equal to m log z. Suppose here you call this as minus m log z. So is it meaningful because there is no water there? Or actually, even if the water that is present, because of the hurdle, will it have the same complex potential and same flow at this position? Yes or no? Right? So here it will not have any impact on it. Now for our analysis purpose, if you wanted to treat this aspect, what we do is we will try to introduce one more source. So one more source exactly at the same distance on the other side. Then here actually again there is one more source of strength m is located exactly at the same distance. Now, because of this, again, the sources actually try to produce these streamlines in all the directions the way it produces on the other side, right? Now here, because of this source and this source, these two will, so together, will try to make the flow exactly tangential to the surface of the wall. Correct or not? So here, by introducing one more source on the other side, these two together will assure the flow or the streamline's direction on the wall of the streamline, also on the wall of the dam. Got it? So on the wall of the dam, if you notice, the fluid will go exactly perpendicular to that, or actually it is tangential to the surface. So there won't be any flow perpendicular to this surface. That means the fluid cannot cross this wall at any instant, right? So this assurance from the mathematical point of view, you wanted to assure that the flow is perfect even here also. For that, what you will do, you are going to introduce one more source at this location because of there is a source presence at this point, so that my analysis will not go wrong anywhere, even if there is a wall presence. And this method we call as the method of images. So you are introducing the image. So this is the source and that is the image of the source. So treat this as the mirror and then try to introduce there. So there is an image. So these two together will give the complex potential at any location, maybe here, or maybe here. It will give the accurate value. So if you wanted to find out the complex potential here, then from this location how far it is, from this location how far it is, then let us say the coordinates of this is z1, then this is minus m log z minus z1. So if you treat this as the coordinate axis, and then this is z2, then minus m log z2 minus z1. So this is the complex potential at this location. That will be perfect complex potential because the presence of both together will assurance the flow at any instant you can think of. Got it? All these locations, the streamlines or the complex potential or the scalar potential will be perfect without having any mistakes, even though there is a presence of this wall. Because we learned without the presence of any surface, we learned what is the value of the complex potential at any point of time, and what is the fluid direction, that is nothing but the stream function, and what is the equipotential lines. All those things we found with an assumption that there is no hurdle in between. But in certain cases, you may get the hurdles, that is in case of dams, right, where there is a presence. So suppose if you have a steel pipe within the water, then how it is behaving at the surface of the steel pipe. So all such kind of cases can be dealt with the help of only the method of images. This is an abstract concept. So you are introducing new sources so that my mathematical analysis will not go wrong. Got it? So this method we call as the method of images. Got it? Now, taking this into consideration, let us say there is a surface here and this is at minus a, this is at plus a, and I call this surface as a y-axis. So this is y-axis and this is x-axis. So on this actually there is a source of strength plus m here and there is a source of strength plus m here. Then at any instant if you want to find out the complex potential at this location, now here the complex potential will be, so this is m log the potential. I call this point as P and this point as Q. The complex potential due to the source present at P will be W1 is equal to minus m log Z plus A, and then at Q W2 or WP and WQ, so this is minus m log Z minus A. So total potential at any point due to both the sources will be W is equal to WP plus WQ. Then this will be W is equal to minus M into log Z plus A plus log Z minus A. So minus M log Z plus A into Z minus A minus M log Z square minus A square. Got it? So this is how actually you will get the complex potential of the entire system of images. Now here actually this actually x z you can replace with x plus iy and then take it into the r e power I theta format. And then this theta will represent the stream function. This theta will represent the stream function and this r will represent the potential function. So this is the methodology that is getting adapted whatever may be the number of sources that are present or whatever may be the number of sinks that are present. Now at any instant the location, let us say this is the location of z is equal to x plus iy. Then at this location if you wanted to find out the stream function and if you want to find out the scalar potential value there, what you are going to use is, this is the methodology. So here z you can treat as x plus iy and then simplify further and then put it in this format. Separate the real and imaginary parts. So this is nothing but phi plus I psi. So phi is nothing but the scalar potential value. Psi is nothing but the streamlines function. From this relation, you can get it by dividing into real and imaginary parts. Real part will be always pi and imaginary part will always be psi. Got it? Okay. So same thing, if you put it in the polar form, let me analyze the same thing in polar form. In the polar form, same thing. So let us say I call this as R1 and I call this as R2 and this angle is theta 2 and this angle is theta 1. Then you can represent R1 e power I theta 1 from the location of Z minus A. So W is equal to minus M log Z plus A minus M log Z minus A. So this can be represented minus M into log of this one is R1. So R1 e power I theta 1 minus M log R2 e power I theta 2. So theta 2 is on the other side. So that is always treated with respect to the positive x-axis. Now here minus M if you take it out, then log of R1 R2 e power I theta 1 plus theta 2. So this is minus M log R1 R2 plus I times of, so log of e power I theta 1 plus theta 2. Minus M log R1 R2 So this is minus M log minus I times of I theta 1 plus theta 2. So this is this part is the real part and this is part is the imaginary part. So this is nothing but the scalar potential, and this is the stream function. So here, if you notice, if I take psi is equal to minus m into theta 1 plus theta 2, or theta 1 plus theta 2 equal to minus psi divided by m. Now here, for a constant, psi value, theta 1 plus theta 2 equal to constant. Now, this constant, if you treat on this particular point, so from this location, both will have the same magnitude. So that means this angle is theta and this angle is theta. So that is theta 1 plus theta 2 equal to pi for all the points. For all the points on y-axis. Now what it essentially means for us. So if any randomly taken point on the y-axis, so this is making an angle of pi minus theta at this location, sorry, pi plus theta at this location and theta at this location. Now these two sum together, so this angle and this angle together will always be equal to pi if you take any point on the y-axis. What it essentially means for that. So that is nothing but psi is equal to constant line. Psi is equal to constant is nothing but psi value is the stream function, streamline or the equi-streamline equation, that is. So on this surface, the streamline will be exactly tangential to the wall, and that's what we need to assure because of this method of images concept. So we reached our point, right? See, Anjali, so this is z plus a and z minus a is equal to r1 e power I theta 1, r2 e power I theta 2. This is simple complex analysis representation of a complex point on the polar form. So this is the polar form. Now here z plus a. So z plus a is nothing but the difference between this point and this point. So suppose if you take this point, this location is z. Then if you draw a line from here, this is z. And if I draw a line from here, this is z is equal to minus a. Now these two differences, if you take this length, this value will be r1 is equal to modulus of z plus a. And the angle, whatever it is making with respect to the x-axis, will be tan inverse of this height divided by this length. That you are going to get it as the theta 1 value. So that is this angle. Got it? So that is the simple way of representing a complex number in polar form. Nothing more than that. So everybody understood? So we have achieved our point, that is on this wall the streamline should be tangential to the wall surface. So theta 1 plus theta is equal to constant, where this constant is equal to pi, that represents this wall surface. Clear? So this method we call as the method of images. So method of images is used to accurately model the flow, right? Even there are some hurdles or some presence of some other components which are present there. So that is the advantage of method of images. So this is an abstract concept. So here actually there is no source here. We have only one source at this point, but you want the complete analysis without having any difficulty or any false statements. So for that we have introduced one more source here so that my analysis will not go wrong anywhere. So note it down. Okay. See, earlier actually we have modeled the doublet on the x-axis. So minus m here and plus m here. Now what if this is located in this direction? So this is plus m and this is minus m. Now if it is making an angle of alpha with respect to the x-axis, then is it the complex potential same? So here the complex potential is coming out to be mu by z. Now here z can be written as mu by r e power I theta. Now here if you wanted to model the complex potential at this point, so this is mu by r e power minus theta. So this you can model it as w is equal to mu by r into so e power minus of theta minus alpha, because you are tilting this doublet with an angle of alpha. So this is theta minus alpha. That means this is w is equal to mu by r into e power minus theta, sorry, I theta, then into e power I alpha. And this can be further written as mu by r e power I theta e power I alpha. So this is the original complex potential of the function. So this is mu by z into e power I alpha, where the axis of the doublet is rotated for an angle of alpha. So if this is the axis of the doublet, then it will be e power I alpha factor you need to multiply, whatever may be the angle it is. Got it? Summary. So which part you want me to repeat? See this. Here actually we have done the doublet complex potential calculation. That is coming as mu by z. So if it is mu by z, then is it the same complex potential even if I rotate this doublet and in this way? So this is angle alpha. Suppose if it is rotated for an angle of alpha, will it have the same streamlines? Will it have the stream? So will it have the same complex potential, or will it have the same scalar potential, or will it have the same streamlines function? So it's not, right? Because the orientation is different. So if the orientation is different, then in what way these streamlines are getting disturbed? So that's what we need to be analyzing. For that, if you rotate this an angle by an angle, then same thing I have modeled. See, mu by r into e power minus I theta is nothing but the complex potential in the polar form for this function. So this is mu into, so here actually if it is rotated by an angle of alpha, this is shifting the angle. So if you take the coordinate shifting, that is transformation for an angle of alpha, this theta can be treated as theta minus alpha. So then it will be exactly same. So if you put that theta minus alpha in place of theta, what you are going to get it is mu by z into e power I alpha. So I converted into polar form and then use the polar equations for the angles. Then finally I converted back into the Cartesian form. So this is how you are going to get the complex potential for a doublet which is oriented with an angle of alpha. Clear? Okay. So these are the concepts we have to be aware. And then this method of images, even on the circles, sometimes it was asked. Suppose if there is a steel tube that is present, so there actually how these streamlines are getting disturbed. So that's what we need to be analyzing. That is to accurately model the flow around the stream, so around the steel tube. So what are the places where we have to consider the sources, or do we need the sinks, or we need both? So such kind of analysis we have to be doing. Now here, so the method of images concept is dependent on the way any particular wall is present or any particular shape is present. Suppose if I have a wall, then actually I have presented one source here and one source here, then actually I have accurately modeled it. Suppose if I have a pipe like this which is located inside the water, so can I use the same concept? Obviously it's not, because suppose if I treat, suppose if there is a source here, then if I treat source here, then the flow will not be modeled accurately at all these locations, because the way the streamlines are coming are completely different when the wall is present versus when the pipe is present like this. Suppose if I have the wall like this, so water is coming in this way, then will it be flowing exactly in the similar manner? No, because there is a wall here and there is a wall here. So we don't know what is the flow here. For that we have to be modeling with a different set of images. So every shape will demand a different set of images. So every hurdle that is making for the flow will demand a different set of images. So those set of images actually you have to be aware. But in reality, or at least from the UPSC point of view, there are only two different kinds of method of images that are asked. One is with respect to the circle, and then with respect to the wall, like this. So these two cases we have to be aware. So that is also very, very complex level of questions, only these things were asked, because the length of the problem will be very, very lengthy. Clear? Any questions? So with this understanding, I'll give you a problem. You try on your own by taking an assignment. Prove that for the complex potential tan inverse Z, the streamlines and equipotentials and equipotentials are circles. Find the velocity at any point and examine the singularities at Z is equal plus or minus I. So I think you don't touch this examine the singularities part, because that's what actually we are going to deal with in case of vertex flow. So wherein the sink, so a vertex is modeled as a sink. So such kind of cases actually we'll be analyzing this. So first of all, you take the first part of it. Prove that for the complex potential tan inverse Z, the streamlines and the equipotentials are circles. So that's the part actually you have to be solving it. Got it? So that should be easier only. So W is given. He asked us to find out the phi value and psi value, and that actually needs to be the circles. So that should be straight away complex analysis problem, nothing related to fluid dynamics. Got it? So with this, I'd like to stop the class for today. Yeah. So thank you. Yeah. Good morning.